Okay, we're working on Chapter 6 of Volume 2. This is Gauss's law, and Gauss's law is another approach to calculating electric field lines. In the first example, we used Coulomb's law, and we saw that, especially for two-dimensional and three-dimensional structures, we had to integrate, and that really caused some difficulty if the symmetry wasn't just right. With Gauss's law, we're going to integrate again. However, most of what we do here, we can use the symmetries of the problem to make the integrals very, very simple. So let's first of all define a very important quantity that we need to calculate in Gauss's law, or one of the quantities that we can calculate from Gauss's law, and this is the electric flux. So here's where the fun begins. The electric flux is related to the electric field, but it is actually, I guess the best way you can think about it is it's a product of the electric field and the area. So this is going to be very important because Gauss's law equates the electric flux crossing any surface as being proportional to how much charge is enclosed by that particular surface. So let's go through a few things. First of all, integrals. We do know that integrals can relate to a number of different properties of functions. If we're dealing with a one-dimensional integral, the integral is usually the area underneath the function. If we're dealing with a two-dimensional integral, then we're typically looking at the volume underneath a two-dimensional function. We're going to actually talk about a slightly more complicated situation, and we're dealing with what's known as a surface integral. So it's not so much that we're graphing an integral as we did, or a two-dimensional function as we did right here. We're actually looking at a surface which may or may not be flat, and then we're essentially looking at a particular function that describes an infinitesimal area on this surface. So this is going to be a little more complicated than just one-dimensional or two-dimensional integrals. But again, try to think about the visual aspect of this. Try to think about the conceptual nature of what we're doing here, rather than really worrying about all the crazy symbols that we're going to cover. So first of all, this is the equation for electric flux, and you'll see that electric flux is expressed as, I believe that's a capital Phi. I better be correct about that one. But it's a capital Phi. Sometimes we'll put a subscript next to it, and the subscript E is supposed to express the fact that this is the electric flux. Sometimes you'll see a subscript B there, and that's something that we'll cover later on. That's the magnetic flux. So electric flux is equal to the surface integral, and again, we're basically adding up all the contributions from small sections of a surface, the surface integral of the electric field dot that small infinitesimal area. So again, the electric field lines, we're going to look at them as they go through a particular surface. In this case, they're going through a very small infinitesimal surface we call dA. And again, the product of the electric field and this infinitesimal surface will create an infinitesimal electric flux. And we're going to add up all these infinitesimal electric fluxes to get the total flux through the surface. Confusing enough yet? Gets better. Okay, so let's look at a surface. Let's look at how this equation pertains to that particular surface. Okay. So here's our surface. This is just some generic surface that we're looking at right here. And we can see it almost looks like a porcupine. You got all these electric field vectors coming out of that. Imagine this surface. Imagine all these field lines. And here we're thinking visually about how much electric flux we have here. We can almost think about it as, what is the total of all these vectors put together that are crossing the surface, okay? So electric flux can depend on two things. What is the nature of the electric field? How intense is it right there? And also, how many of these field lines are passing through this particular surface. More surface as you have right here, the more electric flux you're going to have. So we're going to consider this surface first of all. We'll call it the surface S. We have all these electric field lines passing through it. Okay, now let's take that surface. We're going to break it into a lot of different squares. If we're actually doing the integral here, we have to make these squares infinitesimally small, which means the width, which we might call dV, and the length, du, their size approaches 0. Okay? Now if we were doing a computer calculation, a computer simulation, a numerical calculation of this, then we would actually use finite squares, but we'd make them really, really small to get a high degree of accuracy. So in any case, we've got our little area right here. dA, it's du by dV. And now we're not going to just look at how the electric field lines are passing through it. We're going to look at the normal component of the electric field lines. Remember, this is a dot product. Going back to this equation right here, this is a dot product. So when we look at this, we're looking at the parallel nature to the normal vector, or the perpendicular component of this particular vector to the surface, because the normal vector is perpendicular to the surface. So we combine these two things. Again, here's our equation for electric flux, and here's our surface integral right here, which just tells us that we're going to add up all the contributions from all these different squares. Here's the electric field, which is in red, and here, this blue vector represents the normal direction, the perpendicular direction. So, if E is perpendicular to the surface, then it's just E times the overall area dA. Okay? But if it's at a slight angle, we actually use cosine theta, where, again, the cosine theta is used to get the perpendicular component here. Okay? Cosine, we always do adjacent over hypotenuse. Your hypotenuse here is the electric field line. The adjacent component to it is the normal component. So each little square that we saw previously, it is going to contribute some amount d phi, which is going to be equal to the electric field at that square dot dA, or the electric field at that square cosine theta dA. Okay? Now, obviously, we're not going to actually do these integrations, but we will see that they actually simplify to a much better form than what we're seeing right here. So, again, let's say that I am doing some type of calculation where I want to get the electric flux that's passing through the surface S. I would do each calculation for the squares that are present right there. I would then add up each individual contribution. And again, if I took this to the limit where the area went to 0, I would actually be doing an integral right here. But remember, integrals are very much like summations, where you're actually you're doing a summation of all these individual points, infinitesimal areas, if you will. Okay? So again, here is our electric flux equation. We got an idea conceptually of what we're going to try to do here. Again, we're calculating the electric flux. What in fact we're doing here is we're doing a summation of all the individual electric fields in tiny little areas. The nice thing is that in some cases we can actually simplify calculating the electric flux. Now, in this case, let's say that our surface was just a flat sheet. Okay? As long as it's flat, all the electric field lines are passing through the surface at the same angle. Therefore, this surface integral can reduce to something that's really easy to calculate. Once again, I need to add something. The electric field has to be constant across the surface. The shape of the surface has to be completely flat, so the direction that the electric field lines pass through is constant. And in that particular case, our calculation just becomes EA times cosine theta. Okay? In fact, it would actually become simpler if the angle that the electric field lines pass through the surface was completely perpendicular. In that particular case, it gets really easy, and this is going to be most of the cases that we're going to handle when we're calculating Gauss's law. We're going to look at the electric flux for the case where not only are the electric field lines perpendicular, they're constant, and the area is well known. Real simple to do, right? What's your electric field? How many newtons per coulomb? What is your area? How many square meters? Product of the two, you've calculated electric flux. Okay? There are some different techniques, and this goes back to the previous slide. Remember, we had cosine theta in the expression. This doesn't change what's really happening here, but instead of saying, what component of the electric field do we have in the normal direction, this one's saying, well, we can create an equivalent area perpendicular to the electric field line. So let's say that we have this yellow plane right here, and the electric field lines are passing through it at an angle theta. Okay? If we take a normal component of that area to our actual area, what we call A prime right here, the cosine still comes into this equation, and the electric field times the equivalent area becomes my electric flux. Again, this requires that the electric field be constant over the entire thing. Okay, so that's it for 6.1. And again, most of the cases that we're going to be calculating are the case where the electric field is going to be constant across the surface. The surface is going to be well defined, and instead of doing a crazy integral, which surface integrals are not easy, we're simply going to do the product of the electric field times the area.